Hello, my dear students. Today, let us discuss about slope and deflection. We can see that whenever a cantilever or a simply supported beam is loaded, it deflects from its original position. The amount by which a beam deflects depends upon the cross section and the bending moment. In modern design offices, the main two design criteria for the deflection of the cantilever or a beam is used, that is strength and stiffness. As per the strength criteria of the beam design, it should be strong enough to resist bending moment and shear force. Or in other words, the beam should be strong enough to resist the bending stresses and shear stresses. And as per the stiffness criteria of the beam design, which is equally important, it should be stiff enough to resist the deflection of the beam. Or in other words, the beam should be stiff enough not to deflect more than the permissible limit under the action of the loading. In actual practice, some specifications are always laid to limit the maximum deflection of a cantilever or a beam to a small fraction of its span. In this chapter, we will discuss the slope and deflection of the entire line of the beams under the different types of loading. There are the different theories to find the slope and deflection. First, let us see the relationship between moment, slope, and deflection. Let us consider a beam AB which is initially horizontal when unloaded. Okay, if this deflects to a new position A dash B under the load, the slope at any point C is given by I is equal to dy by dx. Means suppose if we consider a beam AB, okay, which is initially horizontal when it is not loaded, but when it is loaded, it takes the new position, that is A dash B here, and it deflects. Okay, the slope at that point C is given by I. The slope is represented by the symbol I, that is equal to dy by dx. Okay, slope is equal to dy by dx. So this is a figure which shows unloaded beam AB deflected to A dash B dash under the load. Now we have to derive the formula to find the slope and deflection. I just inform you how to derive. It is not so important to study that derivation. Okay, usually in small practice and for all the small curvature, ds equal to dx, that is equal to r into di. This is based on this figure. Okay, here this ds is equal to dx, that is equal to r into di. So di divided by dx, that is equal to 1 divided by r. So I is equal to dy by dx. Now if you differentiate this, d square y by dx square, that is equal to 1 divided by r. Okay, now based on the simple bending theory, all of you know the bending theory, m divided by I is equal to sigma divided by y is equal to E divided by r. Here the first and last term is used, m divided by I is equal to E divided by r. So if you write in terms of 1 divided by r, this becomes m divided by ei. Okay, 1 divided by r, that is equal to m divided by ei. So if you substitute this value in equation, this equation, what we will get, m, that is equal to m is equal to ei, this is ei into d square y by dx square, because 1 by r is equal to d square y by dx square. So d square by dx square is equal to m divided by ei. So if you write in terms of m is equal to d square y divided by dx square, that is into EI. Okay, so this equation is called the deflection equation, or this is the basic differential equation for the deflection of the beam. You just remember this: M is equal to EI into d square y by dx square. Now let us see the Macaulay method for finding the slope and deflection. So Mr. W.H. Macaulay devised a method, a continuous expression for bending moment, and integrating it in such a way that the constants of integration are valid for all sections of the beam, even though the law of bending moment varies from section to section. Now we will discuss the application of Macaulay's method for finding out the slopes and deflection of a few types of beams. Okay, so here you have to remember some of the rules. The following rules are observed while using Macaulay's method. The first one is always take origin on the extreme left of the beam. And second point is, while calculating the slopes and deflections, it is convenient to use the values first in terms of kilonewton and meters. Okay, now let us take this simply supported beam with the central point load. So how to find the slope and deflection for this type of beam? Let us consider a simply supported beam AB of length L. Okay, total length is L, and carrying a point load W at the center of the beam C. Okay, so this is a simply supported beam AB with central point load W, and which is at a distance of L by 2 and L by 2. Okay, now what you have to consider, let us consider taking A as the origin, let us consider the bending moment at any point. Okay, so now we will consider this section first, AC section, and let the section which is at a distance of x from A. Okay, now at this point you have to find what is the maximum bending moment. Okay, this is the origin. So how we will write the bending equation at this point? Mx is equal to this. This is RA. RA is equal to W by 2 in this equation because it is loaded at the center. So here W by 2, here W by 2, RA is W by 2, RB is W by 2. So bending moment at this point is RA into X. RA is W by 2. So W by 2 into X. You don't consider the sign because in some books they have mentioned that left side clockwise as a minus. It's not a matter. Just consider mx is equal to W by 2 into X. Okay, as per our sign convention. How we use the sign convention? I usually write like this. If it is like this, then it is plus. If it is like this, it is minus. So here it is moving like this, so it is plus. So plus W by 2 into X. Next, let us consider the bending moment at this point, at the portion, between the portion C and B. Now you have to consider the section here. Okay, let the section is here. Okay, which is at a distance of X from A, which is at a distance of here. This distance is X from A. Okay, now how we will write the bending equation? Here RA into X, that is there here till here, W by 2 into X, RA into X here till here. Now we have to consider. So RA into X, that is W by 2 into X, then this is still here. You have to consider this point from here to here. What is that? W into here, W into X minus L by 2. We want only this distance, right? So that is what? X minus L by 2. Okay, so this is like the equation 1. Now thus we can express the bending moment for all the sections of the beam in a single equation. So Macular's method says what, the bending equation has to be written in the single equation. So now what this equation becomes, mx equal to w by 2x minus w into x minus half. Okay, here the sign convention different they have considered. We'll consider here this is plus and this is minus as per our sign convention. So now this is the equation, bending equation. Now you have to differentiate this equation. For any point in the section AC, stop at the dotted line. You have to write this to stop at the dotted line, and for any point in the section CB, add the expression beyond the dotted line also. So this is first considering the section at one point, and this is section at the other point. So you have to combine this here. So now mx is equal to this equation. Mx is equal to w by 2x plus w into x minus L by 2. Now m is equal to, I have told first only that the bending equation, deflection equation. What is that? M is equal to EI into d square y by dx square. So that you have to substitute here. So mx is equal to EI into d square y by dx square. That is equal to minus w by w plus wx by 2 plus minus here into x minus half. Okay, then integrate the above equation. What you will get, EI into dy divided by dx equal to w x square by 2 divided by 2, so it becomes wx square by 4 plus one constant has to be added, that is Macaulay method. So plus c1 and then this portion minus w by 2 into, because x differentiation of x is x by 2, so that is x by 2 minus x into half. Okay, so what you will get, it may be noted that the integration of x minus half has been made as a whole and not for individual terms for the expression. This is only due to this simple integration that the Macaulay method is more effective. This type of integration is also justified as the constant of integration C1 is not only valid for the section AC but also for section CB. Okay, this is one equation. Again integrate this equation. What it becomes, EI into, if you integrate dy by dx, it becomes y equal to, again integrate this x square, integration of that is x cube by 3, so x cube by 3, so this becomes w x square becomes x cube in divided by 3, 4 into 3 12 plus c1 into constant is multiplied by x when you integrate, so c1 into x plus one more constant you have to add plus c2. Then this equation, again integrate this, what it becomes, x is x square by 2, so if you integrate this you get this equation, EY in is equal to wx cube by 12 minus c1 x minus c2 plus c1x plus c2, and here it is minus w by 6 into x minus L by 2 whole cube. Then it may again noted that the integration of x minus L by 2 square has again been made as a whole and not for individual terms. So we know that when x is equal to 0, y is equal to 0, means when the length x at that point, a point equal to 0, the deflection is 0. Substituting these values in equation 4, we get C2 equal to 0. We also know that when x is equal to L, y is equal to 0. When you substitute in this equation, we get C2 is equal to this value. Why? You know, x is at the support, so that there the length is 0, so x is equal to 0 and deflection at the support is 0, so y is equal to 0. Then x is equal to full distance at the other end b, so that time also support deflection is 0, so y is equal to 0. When you substitute in this equation, you get c1 is wl square by 16. So if you substitute this equation in 3, you get this equation. Simplify, we will get ia is equal to wl square by 16 14 EI and IB is WL square by 16 EI. When you substitute in deflection equation, you get YC is equal to WL cube by 48 EI. This is the standard equation for slope and deflection. I hope all of you understood. Thank you.